So let's define formally what a linear model actually is. So let's say that we had a response variable y and three regressors x1, x2, and x3. A very general way of modeling the relationship between these variables is that the response is some function of the three regressor variables plus some error. So f is an unknown function, epsilon is our error, and the problem with this so-called model is that f is way too general. How would we estimate anything about the relationship between the three regressors and the response? We have no hope of being able to do that. So it's quite common in statistics to assume a linear model, which in this particular case means that the response is equal to an intercept plus a linear combination of three regression coefficients in each regressor variable plus our error. So beta naught, beta 1, 2, beta naught, beta 1, beta 2, and beta 3 are the regression parameters or regression coefficients. Beta naught is still our intercept. And by assuming that our model is a linear model, it reduces the problem from estimating an infinite dimensional f, so infinitely many possible parameters, to a problem where we only have to estimate 4 parameters: beta naught, beta 1, beta 2, and beta 3. And one of the things I want to emphasize here is that this is a linear model because the parameters enter the model linearly. In other words, the parameters are a linear combination. Our linear model is a weighted sum of the regression parameters and then our regressor variables. So this is not linear because this model is actually going to look like a straight line. It's linear because you can represent it using linear algebra equations and formulas, as we'll see later on in this chapter. So here's another example of a linear model. Y equals beta naught plus beta 1 x1 plus beta 2 log x2 plus beta 3 x1 x2. So once again, the parameters enter this equation linearly, but the regressors do not necessarily enter linearly. So for example, this is the log of the regressor. This is a product of two regressors. And so it's a linear model because the parameters enter the equation linearly. So here's an example of a nonlinear model. Y equals beta naught plus beta 1 times x1 to the beta 2 power plus epsilon. There's no way of writing this as a linear combination of the regression parameters. It's just not possible to do it. So this is a nonlinear model. However, what is interesting is that some models are linearizable, which means that they become a linear model after some sort of transformation. So if you look at this equation down at the bottom, y equals beta naught times x1 to the beta 1 power times epsilon, if you take the log of that, then it actually becomes a linear model. So we had y equals beta naught, beta 1, beta naught times x1 to the beta 1 power times epsilon. If we apply the natural log function to both sides, we get the natural log of y equals the natural log of beta naught plus beta 1 times the natural log of x1 plus the natural log of epsilon. And even though this looks a little different, this is just some response. This is just some intercept. This is our normal beta 1. This is our regressor. And then this is our error term. And so even though it looks a little different than what we had before, we were able to linearize this nonlinear model so that we could represent it as a linear model on the transform scale. So what this means is that in general, a regression model is linear if you can write it in this following general form. So we have a response equals a constant multiplied by beta 1 plus a constant multiplied by y is equal to a constant multiplied by beta naught plus a constant multiplied by beta 1 up to a constant, p minus 1 constant, multiplied by beta p minus 1 plus epsilon, where c naught up to cp minus 1 are coefficients related to our regressor variables. So we're using a slightly different format so that we can generalize this equation, but any regression model that can be written in a form like this is a linear model. So this may be surprising, but linear models are actually very flexible because of the way our predictors or regressors can be transformed and combined into new models. So linear models can be expanded and modified to handle very complex data sets. Linear models can be curved in space, and nonlinear models are rarely necessary. So if you want to fit a nonlinear model, it's usually because you want to do that, not because you actually have to do that. Most of the time, there is a linear model that will suffice for the problem at hand. So let's look at some examples of linear models. So a first order regression model is just a typical regression model that has p-1 predictor variables. So we have this linear combination of our regression coefficients multiplied by our predictor variables. Polynomial regression is a situation where you actually take square terms or cubic terms and higher terms of your predictor variables in order to create your regression model. So let's let x2 equal x1 squared. Then another example of a linear model is y equals beta naught plus beta 1 x1 plus beta 2 x1 squared plus epsilon. And so even though this is actually going to be curved, if we plot it, it still fits this form right here, and so it is in fact a linear model. You can actually have linear models that have qualitative predictor variables or categorical predictor variables. And so you have to use something called an indicator variable to actually fit the model, but you can actually fit linear models that involve categorical variables as well. Linear models can include transformed variables. So in this case, we have log of the response, or the inverse of the response is equal to a linear combination of the regression parameters. You can have interaction effects in a linear regression model. So this would be a situation where for one of the regression coefficients, we multiplied it by a product of two or more of our predictor variables. And so this last example right here would also be an example of a linear model. So here are some examples of linear models where we only have a single regressor. So these are simple models. Actually, in this case, we don't even have a regressor. This is not even simple linear regression. This is called the null model. So we have a constant mean model. We have a simple linear regression model. We have a transformed simple linear regression model, where instead of having x, we have log x. And another simple transformed linear regression model, where instead of having x, we have x of x. And so these models are not linear because they're all necessarily a straight line, as we'll see on the next slide, but because of the parametric form the models have. And so I'm going to plot each of these models without error in the next plot. So basically, I'm not going to worry about the epsilon term here. I'm just going to plot this part, and these parts right here. And so you can see that two of these are straight lines. So the constant model is a horizontal straight line. We have the standard linear regression model, which is this straight line right here. But then we had one that had the regressor x of x. That's one that curves up here. We have another one that had the log of x, which is the one that sort of curves like that. And so even though these are not necessarily straight lines, each of the models that we just looked at are in fact linear models.